afternoon, everyone. It's a real pleasure to be here. I've almost managed to come to AWEC conference. I missed last year, unfortunately, but yeah, at least I'm here this year. And yeah, it's a real pleasure to see people that I met in 2009 for the first time in Chico, and continue to work on this technology. So it's really great. I'm going to give you a bit of an overview and history over our project in Switzerland, which we call Swiss Kite Power. We're a collaborative group, a number of technical universities and universities working together. So I'm from Houle, Nordrhein-Schweiz. We're a technical university in Windisch. We have our colleagues from AWEC, the Material Testing Research Center, as well as our university partners from ETH and EPFL. So other groups here will also be all giving talks. We have industrial sponsors, lucky enough from Alstom and Festo, as well as significant Swiss federal money to help us pursue our project. So, yeah, just to give you an idea of where I got started here, I guess it was around 2008, I started reading in various articles and publications and online about this new kite power technology. Of course, I got very excited being a mechanical engineer and kite surfer. I thought this was a great way to kind of combine interests and passions. And a few months later, I found myself in a boardroom looking into the faces of some confused executives at Alstom, and I was trying to explain this new emerging field of airborne wind energy, showing different pictures from around the world, and trying to get them enthusiastic. Luckily, there was a few people in there that thought this was actually interesting to look into, and we decided, okay, let's try to organize a project. And what they wanted me to do, or what we felt was really important, would be to develop a vision of what we thought kite power could be. So what the system could look like. And in this process, we devised a few questions that we thought were important to answer. So I mean, in the end, we're all trying to put something high in the sky, and it should collect energy. And of course, we have to decide exactly what this should look like. The power, of course, needs to be transmitted down and turned into something that can be sold. So obviously, we need a solution here. Of course, there's the operational issues, which yeah, we all have to deal with. And I mean, at some point, we need to build this somewhere, find some customers, find some markets, and that's really how the industry works. And of course, in the end, what everyone wants to do is produce cheap energy. So in my talk, I'm really going to focus on these two issues. My other colleagues, so first of all, Rolf Luxinger from EMPA, will give a good talk tomorrow morning, the AM, about exactly this process, how we've gone from the kites that we can buy to what we have now. And my other colleagues, for example, Aldo Zakraki and Lorenzo Fagiano, will be discussing and presenting their control systems and flight strategies. Okay, so for me, coming from a kite surfing background, basically looking at all the systems, I thought pumping, winching, this seems like a relatively straightforward way to make power. So somehow that track really started off, and it still seems to make sense in our eyes, so we're going to stick with that. In the end, these questions around pumping got a little more specific. For example, you know, if we can go buy a kite, how much power can we actually produce with it? Could we calculate the same thing? And of course, you know, if we're going to build this together, what are the practical challenges to realizing this? So I'll just show you a quick video. So this is basically after about 2 years of starting off with student projects, small amounts of money, and really trying to just build something together and fly it and see what we can measure. beautiful Alp in Switzerland, we also managed to measure some data. So similar to what you saw in the previous talk, here's our measured power production during that flight. So you can see the tether oscillating about 150 meters. We had about 10 meters per second wind speed. And here was the measured energy production, also mechanical, I have to say. And if you work this out, you come out to about 1 kilowatt average power production. So, I mean, in the end, actually, yeah, not as good as we hoped. Based on some relatively simple performance calculations, we were able to devise basically a simulated power curve for a device, which you see here. And actually, in the end, what we measure, these different points, wasn't too bad at the low end, and at the higher end, you know, we're 50%. So actually, we're getting relatively close to what we can do with this off-the-shelf Kite. So that was an interesting start. And then we continued the project in the past 2 years, and here focusing on different challenges such as automation, and really having a system that we can fly in all weather conditions. And so I'll give you another short video of where we all are now with the experimental testing. And this is basically running a controller from the guys at ETH, Lorenzo and Aldo, on our program. So these are fully automated public cycles, so no one's flying the whole time. Having fun in the Swiss Alps. So, based on this experience, one issue, of course, is using these off-the-shelf kites. Still not really producing any power. I mean, it's in the kilowatt range still. And in terms of the practical challenges that many of you probably have also faced in your testing, you can see we've transitioned from this control pod architecture to a ground-based actuation. This makes life much easier. Of course, it has its trade-offs, but for having a small system to go and test, it's really nice. Of course, all the automation, communication, sensors, everything's software. People have worked on this stuff, you realize how long this takes to really get it working. And of course, also just having a good test site where you're allowed to fly, where you get good wind, that's close to you. These are all things that make something that should take a month, take 6 months, and yeah, but I guess that's just how it is. So I'm going to switch gears a little bit here and talk about cost of energy. So you guys who thought you could avoid the boring part by not going to the finance section, I'm sorry to disappoint you. So I have to say, much of this work on energy cost was done by Jan Salman, who's here in the front, as part of a master's thesis, and as well in the preparation of the chapter for the textbook. So if you want to read about it, there's a textbook chapter by Yanis and myself, so please do so. So I'll start a bit by discussing the LCU metric, just so we're all on the same page, as well as how we went about costing out a large theoretical system, the performance estimation, and then give a few kind of hints of what we think are really important aspects for an economical system. So, LCOE. I guess I don't have to say too much on this. Basically what we're trying to do is collapse the full cost of the system over its lifetime into a simple metric to compare with other technologies. So taking the capital costs, amortizing it over the lifetime with some sort of interest rate, return on investment, for example, as well as adding the O&M costs and dividing by the annual energy production. So just to give a sort of baseline, this is some data published from Lazard, that's an investment bank, recent numbers. So we have something like 1,300 euros per kilowatt range, 25 euros per kilowatt per year O&M costs, and a decent capacity factor. And basically, if you crunch all these numbers, you end up at about 50 euros per megawatt hour, or about 5 euro cents per kilowatt hour. So just to give an idea of the mid-range of what's possible with current wind turbines at the moment. So with this system, basically there's two ways that we can look at the costs. We could start really with the design and build the materials and go get estimates for the whole system. And for a small thing, we think we could do that, but we really wanted to look at a big system, so in the range of 1 megawatt sort of range. So we looked at these costing functions. There's a lot of really interesting work done by NREL on wind turbines. And we basically divided the whole system up into 5 components. So you have the Kite system, which is kind of equivalent to the rotor blades. You have the whole mechanical power conversion, so winch, generator, gearbox, which is basically the same on the wind turbine. We replace our tether, or tower with the tether. The electrical power conversion is roughly the same, and then you have the balance of station. And so basically we kind of adapted the NREL calculations to our system. You can see here, maybe it's a little more complex costing formula, say for the Kite, than what you saw this morning from Adrian and Fraunhofer. And this takes into account, for example, scaling effects of the wing. So those are all those. Just to give an idea of what this comes out with, when we plug in our 1 megawatt size stuff, we end up around, something like 700, 700 euros per kilowatt range, so a bit lower than the 1,000 euros per kilowatt he was talking about. And the performance estimation, basically it's relatively simple analytical formulas adapted from Lloyd. Very good article by Rolf Luxinger in the Airborne wind energy textbook, elaborating on these, so if you want to get more info. And probably the key thing to highlight here is that we're assuming that basically during this recovery phase, that the drag on the system is just the Kite's drag. So basically we're assuming we can fly this figure of 8 going outwards, and then we can pull the Kite back basically as quickly as we want to. And just in terms of optimizing the system, getting good economics, we really see this as a key factor. So the overall plant that we analyzed, we're looking at basically a 50 megawatt farm, really to compare to the NREL data we had available. We derived kind of an analytical function for the spacing between the different machines. So basically we decided we wanted to have the kites flying within these kind of projected triangles, going downwind at some elevation angle from their ground stations. And basically you can play with this elevation angle to get a trade-off between the spacing and the cost of energy. Basically the Kite is 150 square meters. Now, I mean, this isn't something that we obviously currently have, but in terms of performance technology, it's somewhere in between, I guess, what SkySails would be producing versus what Apex is looking at. So we have something like 300 kilonewtons loading, and if you look at the power output, we're sort of in a mid-range. So not quite as high as what Rich's is talking about with 20 kilowatts per square meter, but much higher than what we're seeing with the conventional Kite technology. The other thing maybe to highlight is this asymmetry factor. So basically what this means is we can retract the Kite 4 times as fast as it would go out. Also very key in the optimization. So basically we run this through and we end up with such a power curve. So you can see we're just almost getting our 1,000 kilowatts electrical, of course. And we can see 3 zones. So we have this unconstrained zone where basically we're just trying to optimize power, kind of going at this, roughly this Lloyd, maybe a quarter of wind speed reload. And then we have a force constrained zone where we hit the force limit of our system. And then you see the power zone sloping down. And then in the power limited zone, we're basically just trying to not break stuff or not fatigue or tether, for example. And you see some slight decrease there. So when it's all said and done, you basically get a graph like this when we run over the average wind speeds. And basically you see the capacity factor ramping up to 50–60% at the high end, which would be good. And the LCOE coming down to around 40 euros per megawatt hour. So in the end, unfortunately not much better than what those turbines are doing, but we see this more as trying to understand what key things we have to tune to get a system in that range. Maybe a little more important or more interesting would be looking at the productivity. So how much energy you produce per year per square kilometer. We have our wind turbine baseline down here at about 20 gigawatt hours per year per square kilometer. And basically by varying this elevation angle, we can actually increase, at the cost of slightly higher cost of energy, we can increase our productivity of our pumping Kite plant to possibly 10 times what you can do with a conventional wind farm. So we think that's a very interesting result. And just basically to highlight the final key parameters in the sensitivity analysis that we did. Basically, most important is wind speed, of course, built somewhere windy. Next thing are Kite parameters, specifically CL max, as well as L over D. The Kite lifetime is a huge driver, as well as the winch design. For example, the traction efficiency, and also this winch to tether ratio we were talking about before to prolong the life of your tethers. So, in the end, very simple recipe for low cost of energy. Find a windy spot, build an efficient, long-lasting Kite that you can depower and retract very quickly, and of course build a good winch so you don't destroy your tethers. So here, just to say a final word, I didn't talk anything about the new Kite development. This will be done tomorrow in the morning by my colleague Will Flixinger. I'd encourage you to attend his talk, and yeah, thank you very much.